Good afternoon, everyone. This is Mr. Couple. Today I'm going to be teaching my IB Physics SL Year 1 class about heating power. I have one student in the text chat, but there's no one in voice chat today. So we'll see if anybody shows up while we're recording this. There are three main ideas I'm going to be discussing today. They are, here we go, power is the rate of energy transfer. So we'll remember back to when we studied in mechanical energy, we talked about this quantity called power. We'll be referring to that again today, but this time in regards to heating. The second main idea is that specific heat can be determined from the gradient of a temperature against time graph. And then lastly, this is sort of this weird idea is that if an object is radiating as much power as it's absorbing, or I should say heat, then that means it'll have a constant temperature. So if an object is absorbing energy, heat, as quickly as it's releasing it or giving it off, then its temperature is going to be constant. So those are the three main ideas. Let's get started. First, I want to look at this situation of heating water. So you imagine that there's a beaker of water placed on a hot plate. So we would have actually done this experiment in our classroom. Obviously, we can't do it now, but the idea is that you take this hot plate. So the hot plate is the thing down here at the bottom. You can turn up the temperature. It's kind of like a portable stove. And then we're going to stick a beaker of water on top of the hot plate. And then we're going to have this temperature probe that's going to be pushed into the water. And it's going to be digitally collecting the temperature data at known increments of time. So over to the right-hand side, we can see that every minute that passes, we record the temperature of that the probe is recording of the temperature of the water. And then it creates this nice little graph showing us the temperature and how it varies across time. So here are some questions that we're going to be looking at. So question one, suggest a reason why the temperature of the water reaches a maximum value. So you can see that once we hit, what is that about here, like at 8 minutes or so? Like once we hit 8 minutes, the temperature ends up becoming constant, that it's not getting hotter at that point. So even though we're still supplying heat to the water, so we're still dumping heat into the water, the temperature is not increasing. And so we need to suggest a reason why this might be happening. And so the answer is to think about that energy. So the energy of the water has two parts to it. So the first part is it's the average kinetic energy of the particles plus the interparticle potential energy. So what's happening is only one of these is determined by the temperature. And so the kinetic energy, that's what determines the temperature. So what we're doing is we're increasing the energy without increasing the temperature, which means that rather than increasing the temperature of the particles, rather than making the particles move faster, we're actually going into making the particles separate from each other to pull the particles apart. So that's the potential energy. So what's actually happening here is that instead of speeding up the particles have sort of reached this maximum speed where they can't gain any more kinetic energy, like they're kind of bonking into each other. And so until we can pull them apart, until we can separate the particles, then they can start to go faster. So what's actually happening here is we have a phase change. What we mean is that the liquid water is turning into a gas, it's turning into steam. So the reason the water is at a constant temperature is because the energy that we're adding, the heat that we're supplying, is going into potential energy to pulling apart the particles, going into changing the phase from liquid into steam, rather than speeding them up or making them move faster. Second question: identify the overall. Oh, where's my calculator? There it is. Identify the overall trend in the rate of change of the temperature of the water before it reaches its maximum temperature. So if we look at just this area here, we'll notice that the trend, the rate of change, so how quickly the rate of change is the change in temperature over the time. So if we look at how quickly the temperature is changing, you'll notice that it actually is a straight line, which shows us that this rate of change is constant. So we can say that delta T, so it's linear, and we'll say that the rate of change, so delta T over time, so the rate of change of temperature is how you would say that, is a constant value. Now you'll notice that it's not perfectly constant. So only in that, like, once it gets going, so it has a little bit of like a ramp up where it slowly builds up in its temperature, and then it has a little bit of like a cooling off up here. But while it's going in the middle region there, it's pretty much constant. You have this uniform rate of change of temperature. And so that's the part that we want to focus on. That's the part where the temperature change, the rate of change of temperature, is roughly constant. So it's interesting to think what's down here. So in the ramp up phase, the reason why the temperature is not constant is because the hot plate is still heating up, like it hasn't reached its like full potential yet. And then at the top part, what's happening is some of the particles have reached that maximum speed, but not all of them have yet. And so a few of them start to not being able to get hotter. And so that ends up slowing down the whole rate of change of the temperature until you reach that constant where none of the particles are able to get faster. So what we want to do now is use a little bit of math and show that assuming that the heat supplied is constant, so we're constantly adding the same amount of heat to the water, we want to show that the rate of change of temperature will be constant. So what we're saying is that if the power is constant, we want to show that delta T, change in temperature over time, is also going to be constant. The way we can do this is by thinking about the definition of power. The definition of power is energy over time. But we don't really talk about energy. We talk about a more specific form of energy when we're doing thermal physics. We talk about heat. So that means that the energy is actually mc delta T. That's the heat that we're adding to it. So now we can see that our rate of change of temperature is right there. So there's our delta T over T. So all we have to do now is just divide both sides by mc. So if I divide both sides by mc, I'll just do it like this. mc here and then divide by mc here. We get the result that delta T over T is equal to P over mc. And we said that we were assuming that the heat supplied is constant. So the power is constant. That's the power on top. And we also assumed that the mass was constant and the specific heat is constant. So that shows us that the heating rate, as long as the power is constant, the heating rate, like that delta T over T, the rate of change of temperature, should also be constant. And this is only if P, M, and C are constant. So that's the main idea of this lesson. So now we're just going to be doing a bunch of worked examples using this equation and using these ideas of power and heat. I'm going to check to see if anybody typed anything in chat or what's going on over here. Nope, I'm still all by myself. Well, Laura's listening. Hi, Laura. All right, so here's the first question. So we have same thing, a beaker of water on a hot plate. And here's our available data. So we have 120 milliliters of water. We have an initial temperature of 23 degrees Celsius. We have a specific heat of water as being 4,200 joules per kilogram per Kelvin. And then we have a power output of the hot plate of 300 watts. So the hot plate is capable of transferring 300 watts. So it's taking the electrical energy that we're feeding into it, and it's releasing 300 watts of heat power output from the hot plate. Okay, so part one, it says calculate the amount of energy which must be added to the water to bring the temperature of the water up to its boiling point. So we know that the boiling point is 100 degrees Celsius. And so we want to raise the water from 23 degrees Celsius to 100 degrees Celsius. So that means that the temperature change is going to be 100 minus 23. And so that's going to give us a temperature change of 77 degrees Celsius. So we want to figure out how much heat do we need to supply to the water in order for it to experience a 77 degree Celsius temperature change. The second thing that's important is that the volume of the water is 120 milliliters. What's the mass of the water? And so this is an important thing to know, is that for water, this is how we define it. For water, so water, 1 milliliter is 1 gram. So we could rewrite that we could say that 1 liter is 1 kilogram. So a liter of water has a kilogram of mass. All right, so if we do this, it looks like I am completely running out of space here. I didn't leave myself enough space. Let me move this down. All right, so we can use our straight up equation, Q equals mc delta T. And then we just have to plug these numbers in. So the mass of the water, since it's 120 milliliters, each milliliter is a gram. So we could say that that's 0.120 kilograms times the specific heat, which is 4,200 joules per kilogram per Kelvin. And then we have a temperature change of 77 Kelvin. Once again, when you have a change in a temperature, the unit can be Celsius or Kelvin. They're equivalent. So a 77 degree Celsius temperature change is equivalent to a 77 Kelvin temperature change. And so if you multiply all this together, that's why I have the calculator over here. So let's do it. So we're going to have 0.12 times 4,200 times 77. So we end up with 38,808. So I will call that 39 kilojoules. So we have about 39 kilojoules of energy to bring this water up to its boiling point. Now that's not to boil the water. That's going to take a ridiculous amount of energy. We just want to know how much energy does it take to raise the temperature of the water to its boiling point. We'll talk about phase changes and the energy required to actually physically boil the water. We'll talk about that in the next lesson. So that'll be on Thursday. Okay, next question. Determine the time in minutes that it'll take for the water to reach its boiling point. So this is going to come from the power. So power is energy over time. So if we want to find the time, we just need to rearrange this equation, and we'll find that the time is the energy divided by the power. We know how much energy we need to add. It's 3,900 joules. And we know that the power output was up here. It was 300 joules per second. 300 joules per second. Oh, you know what? I forgot to show that the units up here work out to give you joules. So you can see the kilograms will cancel out here and here, and the kelvins will cancel out here and here, and then we're just left with joules. So that's why we had joules right there. All right, so back down here to estimating the time. So the joules are going to cancel, and we're just going to get a per second, which is just a seconds. Okay, so we're going to get the time is equal to, so we have 39,000 divided by 300. So we'll go over here, calculator, 39,000 divided by 300. We get 130 seconds. So that's about, make a better about sign there. That is about 2.2 minutes. I can turn it into minutes by dividing by 60. So we get about 2.2 minutes. This is a very short time. You are not going to get water to boil on a hot plate in 2 minutes. I've done it before. It usually takes closer to like 15 minutes. So we want to explain why was this an underestimate. So why did we end up getting an underestimate of the actual time? 2.2 minutes is way too fast. This is too fast. So what happened here that gave us too short of a time? And so the reason is because we weren't actually transferring 300 joules. The problem is with the power right here. We weren't actually giving 300 joules to the water. So if we look at my picture up here, that 300 watts, 300 joules per second, that was radiating from the hot plate. That was actually radiating out in all directions from the hot plate. I mean, even like downward. It was radiating out all around it. That's 300 watts. The water on top of the hot plate, put the water right here. The water on top of the hot plate was not getting the full 300 watts. So we'll say most of the power output went to the surroundings. Not to the water. So the water is only going to get a fraction of this. Maybe it gets like 10% or 20%. The water is only going to get a little bit, a partial of this 300 watts. So what we want to do now is figure out, well, how much does the water actually get? And so the way we do that is by looking at this graph. That's the temperature against time graph. So from this graph, we want to be able to deduce the power supplied to the water. So the 300 watts was a drastic overestimate of the power supplied. So we actually want to figure out what the real power supply was. So looking at this graph, we're going to figure out a few things. So here we go. So the gradient of this graph, so like the slope of this graph is going to be how quickly it's heating up. And that's going to be based on the specific heat capacity. Well, since we know that this is water, we know the specific heat capacity is 4,200 joules per kilogram per Kelvin. So that's going to determine the steepness of that graph. We also know that the power, we're going to assume that it's constant. We can see that, just like up above, when we had a constant power, we had a constant steepness of that graph. So we're going to be making those assumptions. So let's figure out what that power was. So just like before, we're going to start with Q equals mc delta T. The difference, though, is that for Q, we're actually going to write it as PT. And so this is coming from the equation that power is energy over time. So if you solve for energy, which is E, you get PT. So we can substitute Q as power times time. So for instance, if we have 100 watts of power and you run it for 5 seconds, then you'd have 5 seconds times 100 watts would give you 500 joules of heat supplied. Just an example of how that works. So down here, instead of Q, we can write PT, and it's the same exact equation, PT equals mc delta T. And what we're trying to do here is we're trying to find the power supplied. So we want to find P. So now all I have to do is just divide both sides by T. So we get P equals mc times delta T over T. And so that delta T over T term here, that's our rate of change of the temperature, which we can find from the gradient. So this term right here is going to be found from the gradient of the graph. So to find the gradient of the graph, we just need to find the rise over the run. And so this is going to require choosing 2 points. So you could try to choose this point here at the end or this point here at the beginning, but reading between those lines can be fairly tricky. Like it looks like it's not exactly hitting right on the line. So what you'd rather do is choose 2 points where it does hit on the line. And then choosing those points will be a lot easier to use than trying to estimate between the lines. So I'm going to pick this point right there since it looks like it's crossing right through the 2 lines. And then the other point I'm going to pick is, which one was it? I think it's this one, because that one looks like it's crossing between the lines too. All right, so if we write down the coordinates of these points, so this point is going to be at 12 minutes, comma, 85 degrees Celsius. And then the other point down here is going to be at 1.5 minutes, comma, 30 degrees Celsius. So we'll use those 2 points and we want to find the rise over the run. So we can see that our rise is just going to be this. That's the rise. I didn't go far enough. And then the run is going to be this. So we just want to find the rise over the run, and that will give us the gradient. So let's do some math. So the rise over the run, I'll just write this down as delta T over T. So we're going to go from 85 down to 30. So that's a change of 85 minus 30. And the change in time is going to be from 12 minutes to 1.5 minutes. So I'm going to do 12 minus 1.5. So if we put this into our calculator, 85 minus 30, I don't need to do that. 85 minus 30 is 55. And 12.5 minus 1.5 is 10.5. So then I'll put that in the calculator. So I'll do 55 divided by 10.5. 55. I always think that it's important to try to avoid using a calculator if you can, because it's always going to be slower for simple things like that. So I get 5.238. 5.238. And now it's important to realize what these units are. So this is temperature change, so that's Kelvin. And then this is time, which up here in the graph was in minutes. So this is kelvins per minute. So our rate of change of temperature is 5.238 kelvins per minute. However, this is going to cause problems because the power is in joules per second. And now we're in per minute. So we want to make sure that we switch this over to per second. So the way to switch this to per second is to just take the 5.238 Kelvin per minute and just multiply it times 60, and then it's going to be per seconds per minute. I didn't do that right. It's upside down. Minutes per second. So there we go. So 1 minute is 60 seconds. So now the minutes will cancel out, and then we'll have it in per seconds. So you just need to take this number and divide it by 60. And then this is my rate of change of temperature in kelvins per second. So that gives us a rate of change of temperature. Delta T over T is 0.0873 kelvins per second. Now, when we plug this back into the equation, it'll give us the answer in watts, which is what we wanted. So we'll just plug that in. So the mass was 0.12. I think that was right. Or was it 240? I'm having trouble. It was 120 milliliters. So the water was 120 milliliters. The specific heat of water is 4,200. And then the rate of change of temperature was 0.0873. And so you put all this together, And we'll get the power as, okay, so here we go. So just need to take my rate of change of temperature and multiply that by 4,200, and then multiply that by 0.12, and I get 44 watts as the power output. So given that it was actually outputting 300, the power plate, the hot plate, the hot plate was giving off 300 watts, and so that's actually only 15% of the energy was actually going into the water. So only 15% was actually going into the water. So that's why we had a huge underestimate for the time it would take, because we were assuming 300 joules per second, but really it was only 44 joules per second. So if we actually redid this calculation, so 39,000 divided by the actual 44 watts, so you end up getting 886. So if we divide that by 60, so that's 15 minutes. Hey, that's what I said it should be. So usually when you have a hot plate like this, this standard style laboratory hot plate, it'll take about 15 minutes to boil a beaker of water. Outline how this result would change if the mass of the water in the beaker were doubled. So what if we had twice as much water in the beaker? So the way to think about this is if we doubled the mass of the water, what would that do? Well, it would mean you'd have to have 2 times as much heat added to it. So doubling the mass would also double the heat. If we want to get twice as much heat, then that means it's going to take twice as much time. And so we can see that over here. If you want to add twice as much energy, it's going to take twice as much time without changing the power. The hot plate has this uniform power output, like it's only giving 44 watts to the water per joules per second of watts. So if we increase the energy we need to add, we're also going to increase the time it takes to add that energy. So that means that doubling the mass also doubles the time it takes. So if we look back up at this equation up here for power, P equals mc delta T over T. And then I'm putting that in parentheses because that's our rate of change. We're calling that the rate of change of temperature. So what will happen is that the mass will double, but so will the time. And these two effects will actually end up canceling out. So we can see that here. So if we have twice as much mass times the same specific heat capacity times the same temperature change divided by twice as much time, then those twos will cancel out. And then we'll just end up with the same exact power as we had before, mc delta T over T. So the amount of water that you stick in the beaker isn't going to affect the power of the hot plate. Obviously, that should make sense. Like if you have a more greater amount of water on the plate, it's not going to affect the properties of the plate. It just means it's going to take longer for the water to heat up. Okay, this is the last question, and then I'm done. So in an experiment, a heater of power 35 watts is used to warm 0.240 kilograms of a liquid in an uninsulated container. It's very important that it's not insulated. So we've got this container, and then it's filled with this mystery liquid. And then what we're doing is we're dumping in 35 watts to this thing, but it's not insulated. So what's going to happen is that heat is actually going to be lost. So this thing is actually going to be radiating power outward as we try to heat it up. So we give it 35 watts, but then it's going to lose a little bit of energy as it heats up. It says the liquid never reaches its boiling point. So then why is the temperature approaching a constant value? So why does it look like the temperature is leveling off here? Like why does it look like it's reaching this maximum? Well, up above, we said the water reached the maximum temperature because it was boiling, because it reached its boiling point, that all the energy was going into the potential energy and none of it was going into the kinetic energy. So the energy that we added was purely going to pulling apart the particles. But down here, that's not the case. For this problem, we're saying it never reaches its boiling point. So what's going on? What's happening? So the answer is that it's because the 35 watts that we're adding is equal to the 35 watts that it's losing. So we're giving it 35 watts. We're giving it 35 joules per second of heat supplied, but it's radiating. It's losing 35 joules per second to the environment. And so the net effect of that is you get a power of 0, that there's no power added. So to just make a note here, we'll say that liquid loses as much power as it is supplied. So the net power is equal to 0. So you could call this thermal equilibrium. I think I said thermal equilibrium. I don't have space to write thermal. Let me move this down. So thermal equilibrium is where the temperature is constant. So thermal equilibrium implies that you have the object gaining as much energy as it's losing, or the rate that it's gaining energy is equal to the rate that it's losing energy. The power input is equal to the power output, and so the temperature ends up staying constant. Now, that wasn't the case for the boiling water. The power input was not equal to the power output. It was getting more power in. That energy, that excess energy that was going in, was going to boiling the water. We'll talk more about this in our next lesson. It's a concept called latent heat, and we'll be discussing that on Thursday's lesson. After the liquid reaches a constant temperature, the heater is switched off. The temperature of the liquid decreases at a rate of 3.1 Kelvin per minute. So there's that rate of change of temperature again that we saw in that previous question. Use this information to estimate the specific heat capacity of the liquid. All right, so we're going to make an estimation, which means that we're actually going to get the wrong answer, but it will make some assumptions that'll cause us to mess things up, but it's going to be close enough. All right, so the first assumption we have to make is that it's going to be this 3.1 Kelvin per minute that it's going to be losing must be the same that it was gaining. So I did that wrong. So the 35 watts, that's what I was looking for. The 35 watts that it's gaining is the same as the 35 watts that it's losing. And so what we're saying is the 35 watts that it's losing is what's causing the 3.1 Kelvin per minute. So the 35 watts is what it's losing causes the 3.1 Kelvin per minute decrease in the temperature. So we know that it was losing 35 watts because the temperature was constant when it was gaining 35 watts. So we're just going to shut off the heat. So the idea is like if we shut off this 35 watts going in, it's still going to be losing 35 watts. Now that's a huge assumption because actually that won't be true. Like throughout, like if we wait a couple of seconds or a couple of minutes, the 35 watts is not going to be a constant rate of loss. You can actually see here because of the curvature of this graph that the rate that it's losing is not constant. But we're going to make an assumption that it is constant. It'll give us the wrong answer, but this is just an estimation. All right, so if we want to estimate this, we're going to start it off by saying that power is Q over T. I'm doing this wrong. Edit that out. No, I can't edit it out. Where I'm looking at my notes and I screwed up. Okay, here we go. Yeah. Okay. So Q equals MC delta T and power equals Q over T. That's what we want. So just like before, we're going to take this Q and we're going to substitute it up into there. And so we'll end up with power equals MC delta T over T. Okay, so here's what we know. We know delta T over T. We know what that is. It was 3.1 Kelvin per minute. We also know what the power was. That was 35 watts. So all we need to know is the mass, and then we can find the specific heat. But we know what the mass is because it said it in the problem. It said that the mass was 0.24 kilograms. You'll notice that it didn't do that in milliliters. And the reason why, because this is not water. If it was water, they could have said 240 milliliters, but this is not water. This is just some mystery substance that we don't know what it is. So we can't assume that a milliliter is a gram because it's not water. So if we solve for C, we can see that C is going to be equal to 35 watts times 3.1 Kelvin per minute divided by 0.24 kilograms. Now the units here are super wacky. We don't want minutes because we have watts. So watt is actually a joule per second. So we don't want a per second and a per minute. We want a per second and a per second. Also, I think I screwed this up, didn't I? Yeah, this is backwards. Man, I'm like off my game today. Let's try this again. So what'll end up happening is I have to multiply by the reciprocal of this. So what I going to end up with is power is going to be, oh my gosh, specific heat is going to be 35 watts divided by, I have to divide by both these things to get it to the other side. There we go. So if we're not thinking straight, we make mistakes. Now I'm thinking straight. Now I got this. Okay, like I was saying before, since the watt is actually a joule per second, we want both of these time units to be per seconds so that they cancel out. So we're going to need to convert this per minute into a per second. The way you do that is by multiplying by 60. So let me just do this off to the side. It'll make more sense. So 3.1 Kelvin in 1 minute. If we multiply by 1 minute is 60 seconds. Here we go. So that's going to give us 3.1 divided by 60. So it wasn't times 60. I had a feeling it wasn't times 60. It's divided by 60. So 3.1 divided by 60. So there's 0.05167. And that's going to be Kelvin per second. Okay, so I need to divide this by 60. So I'll just, where do I want to put divide by 60? I guess, I guess technically I could just put it on top. This is gross. Let's just rewrite everything. Just be clear that way. It's going to take a little bit longer. Sorry if this video goes over time, guys. So 35 joules per second divided by 0.24 kilograms times 0.05167 Kelvin per second. Okay, so now we're good. So the per seconds are going to cancel, and then we're going to be left with joules per kilogram per Kelvin, which are the units of specific heat capacity. So if we do this, we're going to take 35 divided by, open up parentheses, 0.24 times, and I want to multiply by that answer up there. So I'm going to hit second answer and evaluate that, and I get 2822. So we'll say that's 2800 joules per kilogram per Kelvin. Okay, that's it. I'm going to post up the assignment on Google Classroom with a few practice questions that you guys can work on that are very similar to this. If you have any questions, please come see me during my office hours or hit me up on Discord. All right, have a great day, guys. Bye.